Hi, this is Alfawzia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is derivatives of inverse trigonometric function. In this video, we are going to look at the derivatives of the inverse trigonometric function. In order to derive the derivatives of inverse trigonometric functions, we will need the formula. So we are going to relate the derivatives of inverse function. If f of x and g of x are inverse functions, then g dash of x is equal to 1 over f dash of g of x. You have to recall that as well. Two functions are inverses if f of g of x is equal to x and g of f of x is equal to x. Only if this condition is satisfied, we can say that the two functions are inverses. We will go through inverse sine, inverse cosine and inverse tangent in detail in this video. So let us start with inverse sine. Here is the definition of inverse sine. Y equal to sine inverse of x if and only if sine y is equal to x, for this y will lie in between the interval pi over 2 and negative pi over 2. So evaluating an inverse trigonometric function is same as asking what angle did we plug into the sine function to get x. The restrictions on y given on the board are there to make sure that we get a consistent answer out of the inverse sine. We know that there are in fact an infinite number of angles that will work, and we want a consistent value when we work with the inverse sine. So using the range of angles above gives all the possible values of the sine functions exactly once. If you are not sure of that sketch out, you can sketch out a unit circle and you will see that the range of the angles, I mean the y's, will cover all possible values of sine. Note as well that the sine y will lie in between negative 1 and 1. We also have that x will lie in between negative 1 and 1 because sine y is nothing but x. Okay, let's work a quick example here. Here is the first example. Evaluate sine inverse of 1 over 2. So we are really asking what angle y solves the equation. So sine of y equal to 1 over 2. And we are restricted to the values of the y. So from a unit circle we can quickly see that y equal to pi over 6. Am I right? We have the following relationship between the inverse sine function and the sine function. In other words, they are inverses of each other. This means that we can use the fact above to find the derivatives of the inverse sine. Okay, let us start with this one. F of x is equal to sine x and g of x is equal to sine inverse of x. Already in the starting of this video, I have shown the relationship between the inverse function. So that is g dash of x. Hope you remember this formula. So we are just going to use this. I'm going to plug in g of x and find the f dash of g of x. And then I'm going to find g dash of x on this left side. So we got 1 over cos of sine inverse of x. This is not a very useful formula. So let's see if we can get a better formula. Let's start by recalling the definition of the inverse sine function. Hope you know that y equal to sine inverse of x, which implies x is equal to sine y. So using the first part of the definition, the denominator in the derivative would become cos of y. Hope you all are familiar with the trigonometric identity that relates cos, sine and 1. Yes, cos square x plus sine square x is equal to 1. Since I'm dealing with y here, I'm going to use the variable y. Cos square y plus sine square y equal to 1. Let us use this identity in the denominator. I mean, I'm going to rewrite this identity in terms of cos y. I'm going to isolate cos y on the left side and shift all the other terms to the right side of the equation so that I can use that in the denominator. So shifting sine square y to the right side, I'll get 1 minus sine square y. And taking square root, this square will get cancelled out. So using this, the denominator would become sine square of y can be written as sine y the whole square, where sine y is nothing but x. Am I right? So using that, the denominator would become 1 over square root of 1 minus x square. So putting all of this together gives the following derivative. That's it for the inverse sine. Hope you're clear with this problem. Okay, now let's take a look at the inverse cosine. I'll be starting with the definition of the inverse cosine. As with inverse sine, we have got a restriction on the angles y. Y will lie in between 0 and pi only. That we get out of the inverse cosine function. Again, if you would like to verify this, a quick sketch of a unit circle should convince you that this range will cover all possible values of cosine exactly once. Also, we have that. We can say that x will lie in between -1 and 1, and because cos y will lie in between -1 and 1, same as inverse sine. Now let us take an example for evaluating cos inverse. As with inverse sine, we are really just asking the following: cos y equal to -√2 over 2, where y must meet the requirements we just discussed. From a unit circle, we can see that we must have y equal to 3 pi over 4, so that you will get -√2 over 2. Now let us derive the formula for the inverse cosine. The inverse cosine and cosine functions are also inverses of each other, and so we have cos inverse of x equal to x, cos inverse of cos of x equal to x. To find the derivative, we will do the same kind of work that we did with the inverse sine. So if we start with f of x is equal to cos x and g of x is equal to cos inverse of x, we are going to use the same formula that we used. So g dash of x is equal to, so by applying this formula, we will get 1 over negative sine of cos inverse of x. Simplifying the denominator here is almost identical to the work we did for the inverse sine, and so it is I'm not going to show that part. So upon simplifying, we get the following derivative. If you want, I can also show that. It will be negative of 1 over sine y. So I'm going to use the same identity, cos square y plus sine square y equal to 1. So using that, you can replace the denominator, and here it will be negative sign because there is a negative sign here. So the derivative would become, that's it for the derivative of inverse cosine. So the derivative of inverse cosine is nearly identical to the derivative of the inverse sine. The only difference is we have a negative sign here. Hope you're clear with inverse cosine. Okay, now let us start with inverse tangent. As usual, we are going to start with the definition of the inverse tangent. Y equal to tan inverse of x if and only if tan y equal to x. For y will lie in between pi over 2 and negative pi over 2. Again, we have a restriction on y. But please notice that we can't let y be either of the two endpoints in the restriction above, since tangent is not even defined at those 2 points. For the previous two functions, there is some equal to sign below this, but here there is no equal to sign. That's the reason we are not going to consider the endpoints. To convince yourself that this range will cover all possible values of tangent, so you can do a quick sketch of the tangent function, and we can see that this range we do indeed cover all possible values of tangent. Also, in this case, there are no restrictions on x because tangent can take on all possible values. Please notice this. Okay, let me take one example. Evaluate tan inverse of 1. Here we are asking tan y equal to 1, where y satisfies the restriction that we just discussed. So from a unit circle, we can see that y would be equal to pi over 4. Because there is no restriction on x, we can ask for the limits of the inverse tangent function as x goes to plus or minus infinity. So to do this, we will need a graph of the inverse tangent function. Okay, let me show the graph for you. Here is the graph. From this graph, we can see that when limit extends to infinity, tan inverse of x is equal to pi over 2. And when limit extends to negative infinity, tan inverse of x is equal to negative pi over 2. The tangent and the inverse tangent functions are inverse functions. So we can write it as tan of tan inverse of x is equal to x and tan inverse of tan x is equal to x. Therefore, to find the derivative of the inverse tangent function, we can start with two functions, f of x and g of x. F of x can be tan x and g of x can be tan inverse of x. So, by the formula, we will get f dash would be secant square. In the place of x, we have g of x, which is nothing but tan inverse of x. So, g dash of x is nothing but 1 over. So, simplifying the denominator is similar to the inverse sign, but different enough to warrant show the detail. Okay, I'm going to showing the detail. We will start with the definition of the inverse tangent. Y equal to tan inverse of x. So, the denominator would become secant square of tan inverse of x, which is nothing but secant square of y. Again, let us use the fact that cos square y plus sin square y equal to 1. and dividing every term of cos square y we will get, okay, I'll just write it. So if I divide all the terms by cos square y, I'll get 1 plus sine square y over cos square y equal to 1 over cos square y. Sine over cos is tan, so this would be tan square y, and 1 over cos is secant, so this would become secant square y. You can easily derive this identity from the previous identity, and it will also be easier for you to remember. Now, using this expression, you can replace secant square y by 1 plus tan square y. So the denominator would become 1 plus tan square y. Finally, using the second portion of the definition of the inverse tangent function will give us, this would be 1 plus x square. So the derivative is, there are 3 more inverse trigonometric functions. I'm going to show that too. Formulas for the remaining 3 could be derived by similar process as we just did. So here are the derivatives of all 6 trigonometric functions. Here they have used the alternate notation. Arc sine and sine inverse both are same. So instead arc you can take it as inverse. Hope you are clear with inverse derivative of the inverse trigonometric functions. In case if you get any query, you can let me know.